Good morning. Happy Thursday, everyone. What is going on outside? Remember how we had really nice weather and now all of a sudden it's like almost snowing. What the heck? What what is happening? What is this weather? Okay, let's see. I have a couple of housekeeping things that we should chat about. So I was casually reminded on Tuesday that we are in section 4 and that we probably should have a section 4 kind of cumulative test or assessment or something. So I thought a little bit about how I wanted the section 4 kind of like assessment to look. And I thought it would be best because I know hypothesis testing and creating confidence intervals can be kind of a daunting section. I decided to make it more an interactive assignment style kind of final assessment. So it's not going to be a timed test. It's going to have, or sorry, well, it's going to have a time limit, but it's going to have a very generous time limit, I think, compared to some of the tests. And the real key here is that this is going to be an adaptive mode kind of assessment. So adaptive mode means that you'll be able to input some kind of answer, check to see if that answer is correct, and there will be no penalties if you input an incorrect answer. So this gives you a chance to go back, take a look at some of your work, maybe do a little adjustment, find that error, and kind of get the ball rolling in a positive way. So that's what the fourth test is going to look like. I called it an assignment essentially, and it's going to contain three questions, and each of those questions does have some sub parts to it. So basically, the assignment's going to guide you through, I believe, a confidence interval for proportion, I believe. Hypothesis test for a mean, and a hypothesis test for two proportions. So there's three questions. Those are the questions you should expect to see. Each question has its own page. So it has like the statement of the question. A couple of these questions, you'll have to check the conditions. So you'll have to check the conditions on one of the proportions. You'll have to check the condition on the mean. And then on the third one, you get to skip it. So you don't have to check the conditions on the third one. So just to kind of get you a little bit of extra practice doing that stuff before the exam, because all of this is going to be a part of the final exam. And I think if you kind of get used to doing these computations in a more kind of, I kind of consider this a very hand-holdy approach. So it'll tell you like, here, calculate this thing using this formula. Here, calculate this thing using this formula. So I find it hopefully very straightforward. And you have until the start of the final exam to do that. So there's no immediate time crunch on this because I think our exam is on the 28th or something like that, isn't it? I think it's a late exam, right? So you have a little bit of time to do this assessment, to walk through it. And yeah, so you have a lot of time to finish this assessment. And I think it's good practice for what kinds of questions you should expect to see on the final exam anyway. So I think it's a really good practice thing to do. And like I said, it's an adaptive mode kind of thing. So hopefully it'll give you opportunity to do really well on this test. So yeah, like do a little bit of practice before jumping into the assessment. It might be nice to do, an example of, one of each of these things before starting the test from the textbook if you get a chance. But yeah, that's what the fourth assessment is going to look like. It is live, and then the cutoff will be at, 1 o'clock on the 28th, I think, is when our exam starts. It'll X off then. I've also hidden the last chapter. We probably aren't going to have enough time to thoroughly cover the chi-square goodness of fit test. So I decided we're just going to skip that. We're going to finish up the two proportions packet today. And then we'll have next week to kind of go over the two means packet. So, but today let's work on finishing up the two proportion stuff. And we'll probably end a little bit early today to give you guys a little bit of time in case you have some questions about your data collection assignment. So if any of you want to run some ideas past me with regards to the data collection assignment, we should probably do that today or at the latest next week on Tuesday. So I'll try to build in a little bit of time to do that today and next week, Tuesday. When is the test due? So the test is technically due on the 28th by 1 p.m. So like I said, it's I know I realized that you had the data collection assignment coming up next week, so I didn't want to push this into next week as well. And like I said, it's think of it less like a test and more like a timed assignment. It's just going to kind of hold your hand and guide you through the process of creating a confidence interval or creating a hypothesis test for those 3 specific cases. And you will see those on the final exam anyway, so I think it's good practice before jumping into the final exam. Okay, and that's really the data collection assignment and that 4th assignment, that 4th test. Those are the last things due before the final exam. So I will remind you next week to start slowly working on taking a look at those old practice exams and trying to actually, those would be good things to look at probably before even starting the 4th assignment, the section 4 assignment. So it might not hurt to look at some of the hypothesis testing or the confidence interval stuff from that section. Alrighty, so essentially, maybe I'll flash up, let's see, we're not gonna get to that today, but let's talk about, let's just do a little recap of this section. So in this section, ideally what we want to do is take a piece of categorical data that maybe we've divided up into separate cohorts, or what did we call it before? We called it like different strata, for example. Like I've taken a piece of categorical data, I've divided it up into subsections, and I want to test to see if there's a difference between the subsections of this categorical piece of data. So a really kind of nice example might be if I'm working with males and females and I want to see if there's a difference between the male group and the female group. So typically what we do is we do a testing for a difference between these 2 subgroups, or a difference between the 2 percentages that we get inside of these subgroups. So that's what we started discussing a little bit on Tuesday's class. And we can test to see if one group is lower or higher than the other group. It's just a little bit harder to do that when we only have a couple days left in class. So what we decide to do in this particular stats class is just test to see if there's a difference. And so the null hypothesis that we kind of roll with in this case is that there is no difference between these 2 subgroups. So we kind of assume that the proportion inside of subgroup 1 is equal to the proportion inside of subgroup 2, so that those 2 percentages come out to be the same. And we take P1 minus P2 equals to 0 as kind of the center point of the sampling distribution that we're going to be using to compare these 2 groups. Okay, so that's a key thing here. Because the null hypothesis is no change, we're going to take the null hypothesis essentially to be that these 2 subgroups have the same proportion, that there's no difference between the subgroups. So that's where we start with the sampling distribution. And then to get at the standard error or the standard deviation of the sampling distribution, we typically take P1 and P2 and we kind of we take the standard error that we had from our single proportion and kind of add in an adjustment to account for this second group. So the standard error becomes this kind of really messy square root, but there's nothing that we can really do about it. So this is the sampling distribution that we roll with when we want to create confidence intervals or do hypothesis testing when we have kind of 2 subgroups that we want to look at. So notice that it's slightly different from what we were doing before, because before we had a target population and we had a single subgroup or a single sample that we were looking at. So now we do have that target population still, but we've essentially taken a sample and we've divided that sample up into two different subgroups. That's the real key difference that we're rolling with here. Okay, and P1 and P2 are representing those two subgroups inside of that piece of categorical data that we're working with. Now, this slide here did say to create the confidence interval, we typically don't know P1 and P2 from the target population. So we use P1 hat and P2 hat to estimate, the standard error. But usually what we do is one step better. Usually what we do is actually try to pool our data together and create this pooled P hat number, which is I think where we left off in our example on Tuesday. And we use this pooled estimate to try to get a better estimate for the standard error. So it's very typical to, in these particular cases, actually not to use this formula. We typically don't use this estimate here. We typically pool the p-values together, and then we find the standard error using the pooled value instead. So just be mindful of that. We could go either way. Remember that the best case scenario is that we actually know the target P1 and the target P2, in which case I would just use that as the standard deviation. The next best case scenario is actually to use the pooled estimate to calculate the standard error. And if I don't want, if this is really complicated for some reason, or if I don't want to pool together stuff because maybe there's something weird happening between these two subgroups, then kind of the last resort is just to strictly use P1 and P2 to estimate. So what I'm going to be doing today is we've calculated the P hat. We'll go back to that example we were looking at, and we're going to try to calculate this pooled standard error and utilize that, because this is typically the next best thing to actually knowing exactly what P1 and P2 are from the target population. So this is the example we were working on. And is this the alien example? I feel like I saw an Ancient Aliens guide at the bottom right corner. I feel like this is the aliens example. Right, okay, so we have a simple random sample of some college students. And actually I can probably share my other screen right now. So we had a simple random sample. We had 251 females and we had 199 males, and we had a proportion that we had that believed in aliens. So we basically took a success as believing in an alien to get our estimates, our point estimates for P1 and P2. So 185 over 251 for females and 107 over 199 for the males. We check the conditions. I'm not going to go through that, but essentially, if you do need to check the conditions, you just go into each one of the subgroups and check those subgroups separately. So check the sample size condition for each subgroup, check the independence criterion for each subgroup as well. So we were happy with the conditions. We had our estimates. And so we basically started looking at what the sampling distribution is going to look like. So our measure of center we're going to take to be 0. And our standard error we're going to take to be that pooled standard error number, whatever this number comes out to be. So we had, I think, just finished up by looking at how to calculate P hat. And kind of the problem we were running into here was these were not very pleasant fractions. So I kept them as fractions. And even the 292 over 450, I don't think that was a really nice decimal number either. It was okay. But the problem here is with these kinds of calculations, I want to take as much accuracy as I can. So I'm actually going to leave this as a fraction because I know the calculator can handle working with this fraction. So that's our pooled P. Let's go ahead and actually calculate our pooled standard error as well, since we're going to need that. All right, so our pooled standard error is given as this really gross square root. And we're going to take our pooled estimate. So it's always our pooled estimate times the Q hat. It would be Q hat. So it's P1 minus P. And then N1 and N2 are going to be inside of our denominators here. Okay, so just recall that we think of P as the probability of success, and we often think of Q as the probability of failure. So if you do see Qs, if you're doing any reading online, or if you're looking at a formula sheet or the textbook and they're using Qs, just remember that Q is the probability of failure, and we can find that by using 1 minus P. Okay, so this is not going to be super pretty, but we're going to be inputting into our calculator something that looks like this. This one we probably will try to take as a decimal number, because I doubt that this calculation, I doubt our calculator is going to be pleasant enough to give us a fraction final answer for this one. And what was N1? N1 was 251. And I think we had 199 as N2. So this is going to be what we have to program into the calculator. This is going to be the most annoying step, in my opinion. I know that on the assignment that I gave you, these numbers are a little bit nicer, so you don't have to use fractions like this. And I'm hoping that on the final exam, the numbers are nice too. I'll have to double check. Yeah, so hopefully the decimal numbers, hopefully if you have fractions, it's always nice when the decimal numbers come out to be super nice. If you did want to use decimal numbers, I would just kind of err on the side of caution and try to take like 4 or 5 decimal places. Usually if you take 4 or 5 decimal places, you're okay. Where you sometimes will run into a little bit of trouble with these kinds of questions in particular is if you only take like 1 or 2 decimal places, because 1 or 2 decimal places can throw off our probability numbers at the very end quite a bit. So just be mindful of that. If you want to use decimals, it's probably fine. You just want to take 4 or 5 decimal places if it's not a pleasant decimal number. But anyway, I'm going to kind of set up and try to execute this calculation inside of our calculator, which surprisingly, it's very good at handling this kind of thing. So I'm basically just setting up the framework for what I need to do. So I basically have a square root. I'm going to have 2 fractions that I need to add together like so. And then I'm going to start working on some of the easy stuff. So I know that I can throw 199 and I can throw 251 inside of the denominators of these 2 fractions. And then I need to start working on the numerators. So let's get the structure for the numerator. So we need a fraction, and we're going to multiply by 1 minus a fraction. So hopefully you can see that it's, and I just use the arrow keys to just kind of like build up this structure, right? Like I said, it's a little bit annoying, but the calculator is actually quite good at handling getting kind of the bones in that we need. So this is the bones, and just kind of utilize those arrows to kind of figure out, oh, I apologize. No, that works, 292, okay, 292. And yeah, all of these fractions are going to be 292 over 450. Okay, and I like to do just a little 1/over check using the arrow keys just to make sure I'm happy with this, because I really don't want to have to do this again. So that first fraction looks okay. I'm just going to scroll over to the second one just to double check it as well. So that second fraction looks okay to me. The frantic clicking, it's like I'm trying to think of like what kind of game I would be frantically clicking. It's like I'm playing like trying to duel someone on Minecraft or something. I'm just like frantically clicking the swipe button. Okay, so I think that seems pretty reasonable. That's pretty close to what I got in my notes. So let's take 4 decimal places. because that seems to be a nice cutoff point. So 0, 4, 5, 3. It's actually pretty funny that you guys can hear the frantic clicking. I think that's even funnier. So 0.0453. I need to get a silencer on my mouse, apparently. Mario, oh my gosh, I haven't played Mario Party in so long. Okay, and like I said, 4 or 5 decimal places is usually good enough for the sake of this course to help us get as much accuracy as we need. So those really are, that's really the big step, right? So the big steps here, calculating the pooled P, calculating our standard deviation pool. Now we're in pretty good shape to actually start testing a hypothesis. We have most of the stuff that we need. So let's take a look at part 1, which is to construct a 98% confidence interval to test a hypothesis. Okay, this is essentially a normal distribution that we're going to be working with regards to our confidence interval. So we're using a Z star cutoff value rather than a T star cutoff value. We don't need to utilize the student T distribution for categorical data. We're always using the normal distribution. So you can kind of scroll back through your notes or any kind of cheat sheets that you might have getting set up for the final exam. A 98% confidence interval always uses a Z star cutoff number of 2.33. Now, if you didn't know that, there are a couple different ways you could get that information, and I will show you. One of those ways is to actually go into your T distribution chart. So if you are inside of your T distribution chart and you look at, where is it? Right here. So this is a 98% confidence interval. Now, these are all of the T star cutoff numbers in this column, in the 98% column. But if you scroll all the way down to the bottom, you're going to notice this Z star number. So, right, so down here at the bottom, there's this row that says Z star. So we've usually been taking 2 decimal places with regards to the standard normal distribution. If you take 2.33, that's fine. If you take 2.326, that's also fine. I don't really care, as long as you're somewhere in the neighborhood of this number. So that's one way to find that Z star cutoff number. The other way you can find that Z star cutoff number is to utilize the calculator. So you can use the inverse normal command to try to find that Z star cutoff number. If you want to remind yourself or refresh your memory on how to do that, head back to the single proportion chapter where we've done a little bit of work doing that, finding some of these cutoff numbers. So either you know it or you have a way to find this cutoff number depending on what that percentage confidence interval looks like. So we're going to be taking 2.33 and we're going to be utilizing this following formula. Actually, you know what? Let's set up a hypothesis. Well, let's actually, we don't need to set the hypothesis up. We can set the hypothesis up in part 2. Okay, so a CI is given with the following formula. Okay, we're going to take the difference of our 2 proportions, our 2 estimates, and then we're going to add and subtract the Z star number. And in our case, we're going to be using the SE pool method. We're going to be pooling to get that estimate here. Okay, so what was P1 minus P2? So let's try to get this as a decimal number. So P1, okay, let's clear that away. So P1 minus P2. Now, I'm just going to scroll up and grab those numbers for us. So P1 was 185 over 251. And P2 was 107 over 199. Okay, it is going to give us a fraction. I think we're about ready to get a decimal number approximation. So let's take 4 decimal places. So we're going to take, what is this, 0.1994, 0.1994 as our difference. Okay, plus or minus, our Z cutoff number was 2.33. And we calculated the standard error to 4 decimal places, 0.453. Okay, so now we can calculate our lower bound and our upper bound and essentially try to see if we think there is a difference based on these bounds. So that would be our lower bound. Our upper bound is going to be given, of course, by the addition. I don't think you need to see me do that on the actual screen, so I'll just do this on my calculator that I have right here. And I'm just going to take those to 4 decimal places as well. This one did come out to 6 decimal places. So 9, let's go 3, 9. 4, 2, 3. And this one came out as 3049. Okay, so now that we have our range, we want to summarize and make our conclusions. So let's first summarize our interval. So we know that 98% of the time, the true target difference of P1 minus P2 is going to land between these two bounds. And that's, of course, based on the data that we've actually collected inside of this particular survey. Now, if there was no difference between these two subgroups, I would expect 0 to be inside of this confidence interval. That's an important piece of the puzzle here. So if there was no difference between these two subgroups, I would expect 0 to actually be inside of this interval somewhere. However, I don't think it's quite going to fall on this interval. If we take a look at this interval on the real number line, we get something like this. Our lower bound is about 9.39%. And our upper bound is about 30.49%. but our true target is somewhere over here, right? So we expect to see really a difference of 0 between these two groups. And that doesn't fall inside of this interval that we've created. So we've created this, and it's a really big interval too. It's a 98% confidence interval. The fact that 0 doesn't fall inside of this confidence interval is pretty suspect because it's a really large confidence interval. So I would say that and it's not that it doesn't fall in the interval. Like, look how far away it is from the interval too. It's about 9% away from this 98% confidence interval. It's not even like the lower bound is really close to 0, if you know what I mean. Like, it's not like the lower bound is like 0.1% or something. It's that lower bound's pretty significantly far away from what I would expect this target difference to look like. So I would say there's really, really strong evidence here to support the fact that there's actually a difference between how males and females are viewing alien existence. So that is how we might set up and execute a confidence interval for a difference of two proportions. And essentially what we're doing with the difference of two proportions like this is we're trying to see if 0 falls inside of that interval that we make. If it does, then we don't really have much evidence to suggest that there's a difference. But if 0 falls outside of that interval, there's substantial evidence to suggest that there's a difference between the two subgroups. And so that's what we had here, right? 0 falled outside, and in fact, it's very far away, I would say, from the lower bound. So I would say that there's definitely pretty strong evidence to suggest that there's a difference between our two subgroups of males and females in this particular case. How does that feel, guys? Does that feel, does the conclusion feel like a reasonable thing? Did you have any questions about the conclusion at all? We didn't necessarily actually set up our null and alternative hypothesis, but we would definitely be in a situation here where we would have enough evidence to reject the null hypothesis in favor of the alternative hypothesis, in case you're curious. So I don't need to do anything with the calculator at the moment. So I'm just going to pop over here, and that way you guys have a little bit of flexibility to, and that way you guys can use the chat and nobody's going to necessarily see that you're using the chat. Or you can give me a little thumbs up if you're happy. So that's perfect. Perfect. Got a couple of thumbs up. Great. 3 of 13. That's a good proportion. 4 of 13. Hey, there are 4 people listening this morning. That is excellent. Okay, so I'm going to scroll back up. We basically just kind of worked our way through part 1, which is how to construct this confidence interval. What I want to do in part 2 is actually show you how to calculate a p-value the way we normally would using the normal CD function. And we're going to take it up a notch here. Since we used a 98% confidence interval, we're actually going to interpret a probability value, and we're going to compare it to an alpha number. Okay, so we're going to compare it to an alpha number. So in case you're doing any, like watching anything online or reading the textbook, quite often we take an alpha number of 5%. So this is typically what we've done so far with our hypothesis tests. But since we created a rather large interval, a 98% confidence interval, this would correspond to using an alpha number of 2%. So when we go to create our probability number, we're kind of strengthening our evidence by choosing a smaller alpha. So yeah, these two kind of, I guess, are two sides of the same coin. A 98% confidence interval will correspond with us searching for a smaller p-value number. So let's set up and try to do a proper hypothesis test and compare it to 2%. So we're looking at, essentially, we're trying to find 2% or lower would be enough evidence for us to be convinced that there's a difference. That's what this alpha number is telling us. Okay, so if you're wondering about what this means, this just means rather than looking at the kind of standard 5% approach, we're actually going to be looking for a probability value that's 2% or less in order for us to have enough evidence to reject the null hypothesis. Okay, so like I said, industry standards usually 5%, but we're just going to go a little bit stronger here. I don't think there's any need, based on the study that we did on alien existence, is there a need to have such a strong alpha number? Probably not. But I mean, since we made a 98% confidence interval, I might as well show you how to do a hypothesis test with a little bit of a stronger alpha number. So let's actually set up our null and alternative hypotheses. Now, for the null hypothesis, we're going to assume essentially that there is no difference between these two groups. So we are going to assume that the difference P1 minus P2 is 0. So this essentially is no change, right? So this is, we always assume that there is no difference. And then our alternative is always going to be that there is some kind of difference. So our alternative in this case is P1 minus P2 is not 0. So this is no difference between the two subgroups. Versus there is a difference between the two subgroups. So you can kind of see how this ties back into that confidence interval that we made back here, right? If there was enough evidence for us to suggest that there was no difference between the groups, I'd expect that red bar to be somewhere inside of the interval. So this interval that we made up here essentially is telling us where we expect P1 minus P2 to be. I expect it to fall somewhere in between, 9.4 to 30.5%. But 0 is not there. So that's why we're kind of, if I had set up the hypotheses, I'd be favoring the alternative because it appears like P1 minus P2 is not 0. It appears like it's somewhere in between 9.4 and 30.5. So that's how we kind of connect a confidence interval back to the hypothesis test, in case you're curious. But we're going to test this with regards to a probability number instead. So these are the null and alternative hypotheses. Let's see, where do I want to go next? We have a lot of the numbers that we need. We can probably just draw a diagram and get this show on the road. Yeah, so we've done some calculations already. We already know what the estimate difference is. We already know that P1 minus P2 is about 1.1994. 1994, good year. The 90s were great. How many of you are 90s babies? Did you have a good childhood? Were the 90s good to you? I mean, all I can remember is like my Super Nintendo and Nintendo 64 systems, and they were so fun. They were great. $1994 is your birth year. Get out of here. You're a baby. You're a baby. Okay, we calculated our SE pool as well. So I'm just grabbing some numbers from up above. So 0453, 0453. What was your favorite part of the 90s? I'm curious. Do you have any like very fond memories of the 90s? that I don't know. That's hilarious actually. What a fond memory that is. Watching my older brother try to be Slim Shady. Oh man, wow. Wow, 90s rappers. Yeah, Eminem. What is that guy still around? Does he still do stuff? I always find it really entertaining. Well, I find rap to be entertaining in general because I feel like rap has always been marketed by this culture of individuals specifically for like white people. I don't know. I think it's actually quite hilarious to watch that whole scenario unfold. And what rap represents and stands for has always confused me slightly. But anyway, that's a side story. Anyway, I'm glad to hear that good old Slim Shady and his mama's spaghetti is still kicking around out here. Okay, normal with. Okay, so we've checked the conditions already, my dudes. We know that we have a sampling distribution that's roughly normal because of the central limit theorem. And we know a couple things about that normal distribution as well. We know what the center of that sampling distribution should be. It's actually going to be P1 minus P2. So we're assuming that P1 minus P2 is 0. So we're going to take the middle of this sampling distribution to be 0. We also know that the standard deviation of this distribution is about 0.0453. So the standard deviation here, we calculated, we estimated what we think the standard deviation is, and we're taking the SE pool to be that estimate. So let's draw ourselves a little picture. And essentially what we want to do is try to convince ourselves that we know what values to input into the normal CD function, essentially. So here's our normal distribution. We know that the center of this distribution, P1 minus P2, is 0. Now, we went ahead and we collected some data, and we ended up getting P1 minus P2 being about 0.1994. So 0.19, I have no idea where that is, but maybe it's like something like right here, 0.1994. This was the estimate that we got based on our sample. So we're curious about how much probability lives up here. And just to be safe, what we're going to do, since this is nice and symmetric, we can also actually come down here. We can create a similar cutoff number down here. And just to be safe, we can calculate the probability inside of this tail as well. So typically this is what we do. Unless the question specifies to only do a one-sided tail test, we typically take more probability than we need just to be safe. So what we're doing right now is we're going to be trying to calculate the probability that we see an extreme number like 0.1994 or more, or 0.1994 in the negative direction or less. I almost wrote down the probability of peeing instead of the probability of seeing. Yeah, obviously doing too much statistics, too many p-values. Okay, calculate the probability of seeing an extreme value. Also, I feel like it would be painful to pee an extreme value. That would be hard. I wonder if that would be like kidney stones. Okay, seeing an extreme value like P1 minus P2 equal to plus or minus 0.1994 or more. So we can do this. This is a standard normal distribution. So we can do this relatively in a straightforward way using the normal CD function. And remember, when I pull the calculator up, the normal CD function is going to ask us for some information. It's going to want the lower number, the upper number. It's going to want the, I think the measure of center comes first, and it's also going to want the standard deviation. So it's going to want 4 pieces of information. So we need to interpret this diagram to be able to give it those 4 pieces of information, and then the calculator is going to spit back the probability number for us. So let's take the lower bound to be 0.1994 based on our diagram. We can take the upper to be something really, really large, like 100. And we know the measure of center for our distribution is 0, and the standard deviation of our distribution is 0.0453. Okay, so I'm going to bring the screen up. Bada boom. Nope, that's the calculator. Try again. Cha-ching. Okay, so into mode, down into the distributions. Number 3, we're going to click normal CD. Boom. Lower comes up first. Let's put in our cutoff number of 0.1994. Our upper number, just something really, really large. Okay, standard deviation comes first. My apologies, 0.0453. That's our standard deviation. And the center is going to be 0, so I'm just going to leave that as it is. And we get something that looks like this. Okay, that's pretty small. So what is this? 5.3. Let's take 5.37. 5.37. So we get p value 5.37 times 10 to the negative 6. That is hella small. If you want this as a proper decimal number, we would take our 537, the decimals here, and this 10 to the negative 6 just means to move the decimal place 6 places to the left, right? So that's what this scientific notation is telling us. So 1, 2, 3, 4, 5, 6. Decimal place lands here. I'm going to need 1, 2, 3, 4, 5 zeros. So this is a very, very small p-value number as a decimal number. So let me actually just write that in. 1, 2, 3, 4, 5, 5, 3, 7. Now, technically, all we've calculated is one side of this distribution. We've only calculated the right-hand red shaded in region. So what we probably should do here to make sure we don't overstep our bounds is to multiply this number by 2. That will give us both tails. So I'm going to go back into comp mode. We're going to go 1, 2, 3, 4, 5 zeros, 5, 3, 7. Multiply by 2, not that that's really going to change too much. And we're going to get the following. Okay, so we're going to multiply by 2 because essentially we want to get both of the tails. We want to calculate the probability of being more extreme in either direction. And that's going to give us something like 0.1234. And what did the calculator say? 1074. 1074. Okay, I don't know about you, but that's a pretty small percentage. I mean, I probably have better odds of being struck by lightning. In fact, I'm curious, what's the probability of getting struck by lightning? One in 500,000. Let's see what that probability actually is. 1 in 500,000. Decimal number. Okay. Maybe getting struck by lightning is a little bit less of a chance. But still, hopefully that gives you an appreciation for just how far away, essentially, this cutoff number is from the center. This cutoff number of 0.1994 is so far away that it's almost, we're almost as likely to get struck by lightning as getting this cutoff number. That's what I'm seeing. This probability number is so close to zero that we have so much evidence to reject the null hypothesis. There has to be a difference based on, well, I don't want to say it has to be, but there's an extremely likely chance that based on the data we collected, there's a difference between males and females. Does that make sense to you guys? Like, this is crazy. Like, this is such a small probability number that there's no way that we're getting 0.1994 just based on random chance alone. Right? Like, man, I almost have as much probability to get struck by lightning, which is hilarious. Okay, so we have lots of evidence to reject the null hypothesis. Now, what does that mean with regards to the two subsamples we're looking at? Well, this means that the data is suggesting that there is a difference between males and females when it comes to thinking about aliens, right? So I want to make a conclusion based on the p-value and connect it to not only my null hypothesis and alternative hypothesis, but I also want to make sure to connect it back to the actual study that we're doing as well. So usually when we're making a conclusion, I'm going to be asking you specifically on the section 4 assignment to, give me a sentence that's talking about comparing this p-value to the hypotheses. And second, give me a sentence that's kind of connecting this back to the original study. So the p-value essentially is telling us, based on the evidence, or based on the data, sorry, there's probably a difference between males and females. All right, so that hopefully gives you some insight into how to tackle a difference of two proportions. So I would say I do want to stop class here, and that way we have a little bit of time in case you guys want to come onto the mic to ask some questions about your data collection assignment. In case you just want to kind of clarify what kind of test might be appropriate for your data collection assignment. So yeah, so that's it for class today. If you're happy with your data collection assignment, you can peace out. But if you want to stick around and ask some questions, I will be here for at least 20 more minutes if you want to get some questions answered about the collection assignment. Yeah, you're very welcome, Bianca. Have a lovely, lovely weekend, all of you. And we have just one more chapter to get through next week. We're going to be doing the difference of two means next week. And I believe, so we have one kind of big example to do. And then we also talk a little bit about ANOVA next week as well. So that'll connect back to one of the labs that you guys have to finish up for next week. So yeah, if you want to, yeah, you can email me too. Yeah, so yeah, for sure, Jordan, if you have any questions, you can email me over the weekend. I will do my best to respond as quickly as I can to those emails. Yeah, the key is like, if you want to email me, just make sure I have a link to the data or I can see the data so I know kind of how I would think about analyzing the data.
Hello, Professor.
Hello, how are you?
I'm good. How are you?
Not too bad. Yeah, what can I help you out with, Asim?
So I had a question about the assignment.
Yes.
So I remember when I sent you an email, at that time we hadn't covered the related topics in the class yet. So I guess we covered those topics today.
Yes, so your test will look very similar to what we covered today.
Okay. So I just had one question. When are your office hours next week before the assignments are due? Like, do
Next
you have
week,
office hours other than Monday and